Welcome to Index Properties and Soil Classification Systems lecture 5. In the previous lecture, we have studied about activity and we also introduced about soil classification systems, and we have discussed about ASTO classification system and unified soil classification system. In this lecture, we will be studying about unified soil classification system, the classification of coarse grained soils and fine grained soils, basically by using Casagrande's plasticity chart, and then we will look into certain problems. So, this is the lecture with index properties and soil classification systems 5. So, in the previous lecture, we have defined activity value or activity number, and we said that, and this is useful for classifying soils according to their swelling potential. So, whether the soil is susceptible to swelling or not, to some extent activity value will give the information. So, here we said that activity is equal to plasticity index divided by percentage clay fraction. So, in this figure, x axis, the percentage of clay less than 2 microns, that is passing 2 micron in whole sample is plotted, and along y axis the plasticity index of the whole sample is taken. So, based on this chart, by using this chart, one can classify the soils for their swelling potential. For example, if the value is activity value is less than 0.5, then it is said that activity value is less, and 1 very high in this region and activity 2 in this region is very high. So, low, medium, high and very high zones are indicated. So, based on that, once we get percentage clay fraction for the given soil and the plasticity index, then if you plot those values in this chart, we will be able to give the swelling potential of a particular soil. So, to some extent this will give about also the probable clay mineral in the soil. So, in the soil classification, we said that there are list of soil types commonly used for field classification. So, in the field classification, generally we use typical soils based on their origin, like inorganic soils or organic soils and are. So, before introducing the unified soil classification system and plasticity chart, let us discuss about different soil types which are used in the field classification system. So, here in this slide, soils of organic origin are formed chiefly in situ, either by the growth and subsequent decay of plants or by the accumulation of fragments of the inorganic skeletons or shells of organic origin. So, soils of organic origin are formed chiefly in situ, either by the growth and subsequent decay of plants or by the accumulation of fragments of the inorganic skeletons or shells of organic origin. So, soils of organic origin can either be inorganic or organic. So, the soils which are formed with this process can be inorganic or organic. So, inorganic silt is a fine grained soil with little or no plasticity. This generally we come across like inorganic silt, which is a fine grained soil and with little or no plasticity. So, the least plastic varieties generally consisting of more or less equidimensional grains of quartz, so referred as a rock floor. So, the least plastic varieties generally consist of more or less equidimensional grains of quartz, also referred as the rock floor. So, the inorganic silt with the least plasticity with equidimensional grains of quartz is also referred as a rock floor, whereas the most plastic silt contains an appreciable percentage of flake shaped particles and is referred as plastic silt. So, in the inorganic silt, one can be non-plastic silt and then plastic silt. Then one with non-plastic silt is also referred as a rock floor. The one with more plastic silt and flake shaped particles is referred as plastic silt. So, plastic silt is often mistaken for clay. Plastic silt is often mistaken for clay, but as discussed in the previous class, it can be distinguished by shaking or dry strength test. So, if you are able to conduct a dry strength test or shaking, we will be able to distinguish between the plastic silt and a given soil clay. So, in the soil classification here, we have seen the first type here is that field classification system, the inorganic silt, which is a fine grained soil with a little or no plasticity. The one with the least plasticity is referred as non-plastic silt, which is also referred as rock floor. The one with most plastic silt containing an appreciable percentage of lake shaped particles is referred as a plastic silt. The other part we said that the organic silt. Organic silt is a fine grained more or less plastic soil with an admixture of finely divided particles of organic matter. Shells and visible fragments of partly decayed visible matter may also be present. So, in the organic silt, which is a fine grained more or less plastic soil with an admixture of finely divided particles of organic matter, shells and visible fragments of partly decayed vegetable matter may also be present. So, this is an indication, for example, if you come across this particular soil in the field, then one indication is that the shells and visible fragments of the organic matter will indicate a particular type of this organic silty soil. So, basically the color of this organic silty soil varies from light to very dark grey color, light to very dark grey color, and likely to contain considerable quantity of hydrogen sulfide, carbon dioxide and various other gaseous products of the decay of the organic matter, which give it a characteristic odor. So, this organic silt likely to contain considerable quantity of hydrogen sulfide and carbon dioxide and various other gaseous products of the decay of the organic matter, which give it a characteristic odor to the soil. And the permeability of the organic silt is very low, that is the capacity of the water to allow it to flow through the soil is for organic silt is very low and its compressibility is very high. Because of the presence of the organic matter, the compressibility of this organic silt is very high. So, we saw organic silt and then inorganic silt. Then let us try to look into the other type, organic clay. The organic clay is a clay that owes some of the significant physical properties to the presence of the finely divided organic matter. So, organic clay is a clay that owes some of its significant properties to the presence of finely divided organic matter. So, when saturated, organic clay is likely to be very compressible. So, mostly this organic clay, when it is saturated, it is more compressible, and when it is dry, it exhibits very high strength. So, the dark grey to black color is an indication, the dark grey color to the black color is a indication and may have a conspicuous odor. So, organic clay is a clay that owes some of its significant physical properties to the presence of finely divided organic matter, and when saturated, organic clay is likely to be very compressible, but when dry its strength is very high. So, under saturated conditions, the organic clay exhibits very high compressibility, but when in dry conditions it exhibits very high strength, and its color varies from dark grey to black color and may have a conspicuous odor. The another thing is that depending upon the degree of the we discussed that sand, clay, gravel these soils they exist in mixers, and depending upon the proportion sometimes we call silty sand, clayey sand, sandy clay or gravelly sand or gravelly clay or so. So, let us look into how a nomenclature is used to to describe the soil which we come across in the field. If the soil is made up of a combination of two different soil types, the predominant ingredient is expressed as a noun and the less prominent ingredient as a modifying adjective. So, if a soil is made up of a combination of two soil types, the predominant ingredient is expressed as a noun and the less prominent ingredient is expressed as an adjective. For example, let us consider a silty sand, silt and sand with different apportioning mixers. So, silt and silty sand indicates a soil that is predominantly sand, but contains a small amount of silt. So, that is the reason why we are calling silty sand, where sand is here is noun and silty is an adjective, modifying adjective. Similarly, a sandy clay is a soil that exhibits the properties of a clay, but contains an appreciable amount of sand. So, it has got an appreciable amount of sand, but it exhibits the properties of the clay. So, because of this, a sandy clay is called is a soil that exhibits the property of a clay, but contains an appreciable amount of sand. So, if a soil is made up of a combination of two different soil types, the predominant one is expressed as a noun and the less predominant one is expressed as a modifying adjective. So, examples silty sand or sandy clay. So, now let us come back once again to the soil classification systems, and we will discuss the most widely used soil classification system, that is unified soil classification system. And in the previous class, we have discussed about the ASTO soil classification system, which has been developed especially for the highways, roads and highway works. And universally, this unified soil classification system is being used by geotechnical engineers for different applications. So, soil classification again whatever we have discussed, if you look into it, the soil classification is the arrangement of the soils into various groups or subgroups to provide a common language to express briefly the general usage of characteristics without detailed descriptions. So, soil classification is the arrangement of soils into various groups or subgroups to provide a common language to express briefly the general usage characteristics without detailed descriptions. So, we are actually grouping the soils with which are having identical properties. So, for that number of classification systems have been developed and used. So, two most widely soil classification systems are ASTO soil classification system and unified soil classification system. The unified soil classification system and ASTO soil classification system, they are based on the grain size distribution and Atterberg limit properties of a given soil. So, we have discussed that though we are able to determine the grain size distribution of the characteristics of coarse grained soils, but when it comes to fine grained soil, we thought that because the fine grained soil exhibits different physical states with the water. So, with that in mind, we also discussed and determined different Atterberg limits of a soil. So, these Atterberg limits will be able to give unique values for the given soil. So, based on those values and then grain size distribution, we will be able to combine all these properties whatever we have discussed to classify the soil. So, two widely used soil classification systems are ASTO system, ASTO soil classification system and unified soil classification system, and both systems use simple index properties such as grain size distribution GSD, liquid limit and plasticity index of the soil. So, we have discussed that one of the requirements of a soil classification system is that it should be the classification system should be simple and it should be able to do with limited experiments. And further, once the soil has been identified and classified, then extended experiments can be carried out to characterize the soil. So, unified soil classification system when originally proposed by Arthur Casagrande in 1942. The unified soil classification system was originally proposed by Arthur Casagrande in 1942, revised by the Corps of Engineers and US Bureau of Reclamation in 1952. So, this Arthur Casagrande soil classification system has been adopted by Corps of Engineers and US Bureau of Reclamation, and they revised in 1952. Widely used by various organizations, as mentioned earlier, this soil classification system is widely used by various organizations and by geotechnical engineers and in private, in consulting business and building codes. So, different building codes have this particular classification system and is widely used soil classification system by geotechnical engineers. When you look into this unified soil classification system, initially in Arthur Casagrande, when he has given, he has divided the soil into two major types. One is the coarse grained soil and then fine grained soil, and then they are further divided into coarse grained soil as a gravel and sandy soils, and fine grained soil as a silt and clay or inorganic clay, organic silt or clay, but later the revised extended classification system of Casagrande has included highly organic soils like peat and muck, peaty soils or mucky soils also have been added. So, the Casagrande's extended soil classification system, which says that the soil is predominantly divided into a coarse grained soil and fine grained soil and a peat soil. So, a coarse grained soil is further divided into gravel and sand. Coarse grained soil is further divided into gravel and sand, and fine grained soil is further divided into silt, inorganic clay. We have discussed and we have introduced the term inorganic clay, organic silt and organic clay. And the third one, which is again here, is the peat one, which is there, which is peaty soils or muck type of soils, which are if the soil exists in the particular site. We have discussed that the peat soils are highly fibrous soils, which are required to be replaced or to resort to a ground improvement technique. So, when we look into this, the two major divisions were put forwarded in the unified soil classification systems are coarse grained soil or fine grained soil. A soil is coarse grained, gravelly and sandy, predominantly gravelly and sandy. If more than 50% is retained on a number 200 sieve, that is, if 50% of the soil is retained in number 200 sieve. Number 200 sieve as per ASTM is nothing but 75 micron or 0.075 mm sieve. And soil is treated as a fine grained soil, that is silty and a clay soil, if more than 50% of soil is passing through number 200 sieve. So, if a soil is passing through number 200 sieve, that is passing through 75 micron sieve or passing through 0.075 mm sieve, which indicates that the soil is of silty and clay in nature, or which is fine grained in nature. So, two major divisions are a coarse grained soil and fine grained soil, and a coarse grained soil is more than the 50% of soil is retained in a 75 micron sieve, then it is treated as a coarse grained soil. If more than 50% passes through the 75 micron sieve, then it is treated as a fine grained soil. So, soil is further classified into number of subdivisions with the primary and secondary characteristics, and because of the classification system requirement, so groupings have been done with primary and secondary characteristics. So, the following symbols are used in a unified soil classification system, USCS. G indicates gravel, S indicates sand, W indicates well graded, P poorly graded or gap graded, some of the particle sizes are absent. C is well graded with some clay, F is well graded with excess fines. Suppose if you find a gravel with well graded with excess fines, that particular type of this soil predominantly behaves something like a clay soil, because the fines which are present in between gravel particles will not allow these gravels to come closer, and finally they inhibit in mobilizing the strength and all. So, M, that is silt, which is called, the symbol for silt is M. The origin of this in Swedish, mo means that silt. So, that is the origin why that we use M for indicating the silt. C for clay, O for organic, P small t for peat or highly organic soils, and L low plasticity, I intermediate plasticity, and H high plasticity, that is depending upon the liquid limit, that is less than 30, 30 to 50 and greater than 50 liquid limit. This low, I and H are divided. Depending upon whether the soil is well graded or poorly graded, then these are coarse grained soils are divided, and sometimes the gravelly soils can have also some clay and excess amount of fines. In that case, these particular secondary characteristic symbols are used. So, the criteria for the classification of coarse grained soils into basically the coarse grained soils are classified into 4 groups. Later we will see the chart. W is well graded, that is what we have discussed. So, we knew that from the once we know the gradation of a given soil, once you know the D30, D60 and D10. So, we can determine coefficient of uniformity and coefficient of curvature. coefficient of uniformity is D60 by D10 and coefficient of curvature is D30 square by D60 into D10. So, if the Cu value is more than 4 for gravels and Cu is more than 6 for sands and Cc is 1 to 3 with fines for the finer than 75 micron which are less than 5%, then it is called well graded. P is poorly graded when the Cu is less than 4 for gravels, less than 6 for sands and Cc not between 1 to 3. So, if the above criteria is not met, then it is called poorly graded with fines less than 5%. And C plastic clayey fines, Pi the plasticity index is greater than 7 with fines more than 12%, then it is called C, and M non-plastic silty fines with plasticity index less than 4 with fines more than 12%. So, if you look into this, the predominantly 4 groups W, P and C and M. So, the criteria for the classification of the fine grained soils is entirely based on the plasticity chart. This is also developed by the Casagrande for basically this is the part of the unified soil classification system for classifying fine grained soils. What has been done is that the basis of origin of this plasticity chart is the correlation of the number of soil properties of the collected from the throughout the world. So, experimental results from soils tested from the different parts of the world were plotted on a graph of plasticity index as an ordinate, that is on y axis, and liquid limit on abscissa, that is on x axis. It was found that clays, silts and organic soils lie in distinct regions of the graph. So, what has been found out that when these soils are tested from different parts of the world and are plotted against plasticity index and liquid limit. So, plasticity index on the y axis, liquid limit on the x axis, then it was found that the clays, silts and organic soils lie in distant regions of the graph, So, this is this slide shows the Casagrande's plasticity chart. This slide shows the Casagrande's plasticity chart. X axis it is liquid limit, the liquid limit is plotted on the x axis, plasticity index is plotted on the y axis. So, if you see here, the main features of the this Casagrande's plasticity chart are A line it is called Casagrande's A line, and this is called U line, that is Casagrande's U line. So, the correlation, the equation for the A line is plasticity index is equal to 0.73 into WL liquid limit minus 20. So, if you look into it here, some cohesionless soils with low plasticity index and they lie above the A line, and if you see that predominantly this has got 6 regions 1, 2, 3, 4, 5, 6. As you go towards the right, then inorganic silts of high compressibility and organic clays which are below the A line. Inorganic clays of high plasticity, they are above the A line. Inorganic clays of medium plasticity, they are above A line, but in between liquid limit 30 and 50. So, what has been done is that it has been subdivided into liquid limit 30, liquid limit 50. So, for the low plasticity less than 30, medium plasticity between 30 to 50 and high plasticity liquid limit greater than 50. So, some cohesionless soils they fall here, some inorganic silts of low compressibility they fall here, inorganic silts of medium compressibility and organic silts they fall here, and inorganic silts of high compressibility and organic clays they fall below here. So, this is the equation of A line and this is an equation of U line, which is I is equal to IP is equal to 0.9 into WL minus 8, but this is the upper limit for the values which are there which are used for correlation. If our tested values fall above this line, that indicates that we are required to repeat Atterberg limit test. So, let us look into the features of this Casagrande's plasticity chart. So, we have introduced the Casagrande's plasticity chart is developed based on the correlation of the number of soils plotted on the with the plasticity index as on y axis and liquid limit on the x axis, and basically it has been divided distinctly into 6 zones to classify different soils of different origin. So, the chart is divided into 6 regions, that is what we have discussed. 3 above A line, this A line delineates the boundaries between the clays and the silts, that is what it is doing, the above the A line and silts and organic soils below the line and the 3 below. So, the equation of A line which has been obtained after the correlation is IP is equal to 0.73 into WL minus 20. WL is the liquid limit which is expressed as a percentage. So, the chart is divided into 6 regions, 3 above the A line and 3 below the A line, and above the A line is delineates between A line delineates between the clays and silts and organic soils below the line. And U line, that is what we are discussing in the chart, defines the upper limit of the correlation between the plasticity index and liquid limit. If the results of soils tested fall above the U line, then repeat the Atterberg limits. That indicates that there is something error with the Atterberg limit test which have been carried out. So, equation for U line is IP is equal to 0.9 into WL minus 8, which is WL is again expressed as a percentage. So, U line defines the upper limit of the correlation between the plasticity index and liquid limit. If the results of soil test fall above the U line, then it is indication that the Atterberg limits have to be repeated. So, second feature is all points representing inorganic clays lie above A line, and all points for inorganic silts lie below it. So, all points representing the inorganic clays, whether low plasticity or medium plasticity or high plasticity, they lie above A line, or all inorganic silts of low compressibility, medium compressibility or high compressibility, they lie below it. Points representing organic clays are usually located within the same region as those representing inorganic silts of high compressibility, and organic silts in the region assigned to the inorganic silts of medium compressibility. So, points representing the organic clays are usually located within the same region as those representing inorganic silts of high compressibility, and organic silts in the region assigned to the organic silts of medium compressibility. In the doubtful cases, sometimes we will get a doubt whether the soil is really inorganic or organic. So, for that case to verify that, it is suggested to carry out liquid limit test on a fresh and then dried sample. So, if you conduct a liquid limit test on a fresh and a dried oven dried sample, then if the liquid limit, if the drying decreases the liquid limit by 30%, if the drying decreases the liquid limit by 30% or more, the soil may be classified as a organic, because as during the drying process the soil may be subjected to some irrecoverable changes. So, because of that it affects the liquid limit. So, if the drying decreases the liquid limit by 30% or more, then it is indication that the soil is organic. So, in the doubtful cases it is suggested to check by conducting a liquid limit test with sample which is fresh, which is collected from the field, and the second one is that same sample which is own dried and then conditioned to prepare to carry out liquid limit test. In the third feature, as the liquid limit increases on the x axis, if we go towards the right, the plasticity and compressibility of soils also increase. So, if you have seen on the chart, as the liquid limit increases, the plasticity, which is medium plasticity or low plasticity on the left hand side, and it increases to high plasticity. Similarly, the compressibility from low to it increases to high compressibility. So, as the liquid limit increases, the plasticity and compressibility of soil also increases. The dry strength of the inorganic soils represented by the points on lines located above A line increases from medium to samples with a liquid limit less than 30 and to very high for samples with liquid limit greater than 30. So, the dry strength of inorganic soils represented by points on lines located above A line increases from medium to samples with a liquid limit less than 30 and to very high for samples with a liquid limit greater than 100. So, if you look into it, here the plasticity and compressibility are increasing as the liquid limit is increasing on the chart, and the dry strength of inorganic soils represented by points on lines located above A line increases from medium to samples with a liquid limit less than 30 to very high for samples with a liquid limit greater than 100. So, now having seen different criteria for unified soil classification system, let us look into the detailed chart. Then we will try to use this unified soil classification system and try to solve some problems with different gradations and then Atterberg limits, and then to arrive at the soil classification group, whatever we have discussed about this. So, in the Cascade plasticity chart, which is basically used for classifying fine grained soils, which is inbuilt in the unified soil classification system to arrive at soils of different types with a different combination. That means that a clay of low compressibility or silt that is indicated with M, suppose if it is highly compressible, then MH. So, it is like this, the groups have to be arrived. So, in this chart, if you look into it, the coarse grained soils, basically we have discussed that with the percent passing number 200 sieve, that is 75 micron sieve, is less than 50, then it is indicated as a coarse grained soil. And the gravels, the percentage of the coarse fraction passing number 4 sieve is less than 50, and gravels with little or no fines, and gravels with fines. So, these are the different subgroups here. The major division is coarse grained soils. So, we are discussing about gravels with no fines and gravels with fines. The typical names, they work out like this: well graded gravels, gravel sand mixers, little or no fines. It is qualified as a group GW if Cu that is D60 by D10 is greater than 4, Cc D30 square by D60 into D10 is between 1 and 3. So, Cu greater than 4 and Cc in the range of 1 to 3, then the mixer is well graded gravels with gravel sand mixers, little or no fines is GW. So, the gravels which are present of the coarse fraction passing number 4 sieve is less than 50, then gravels with little or no fines, then it is called GW. Poorly graded gravels, that is poorly graded gravels or gravel sand mixers, little or no fines is GP. That means that if you are not able to meet this well graded criteria, then indicates that it is not meeting the two criteria, means Cu greater than C4, Cc in between 1 to 3. If it is not meeting, then it is called GP. Gravels with fines, that is silty gravels, gravel sand silt mixers, it is called GM if Atterberg limits fall below A line. That means that we have just discussed, if the plasticity index is less than 4, then if it is falling below A line, then it is called GM. That indicates that M indicates that the presence of silt, but is a low plastic silt. That is why it is falling below the A line. Clayey gravels, gravelly sandy clay mixers. Atterberg limits of the of this particular soil with the clay fraction soil, which is having a plasticity index greater than 7 and which is above A line. That indicates that clay gravels or gravel sand mixers indicates with GC. So, gravels with fines, the group is now is GC if the Atterberg limits which are falling above A line, limits above the A line with plasticity index greater than 7. Next is that sands, the subgroup in the coarse grained soil. Previously, we have seen that gravelly soils. Now, similarly with the sandy soils, the percentage of coarse fraction passing number 4 sieve is greater than 50, and clean sands, little or no fines, sands with fines, appreciable amount of fines. Sands with fines, that means that the fines indicate the appreciable amount of, so cannot be neglected, appreciable amount of fines. So, well graded sands, like we did for gravels, similarly well graded sands, gravelly sands, little or no fines. If Cu is greater than 6, Cc in the range of 1 to 3, if you are able to satisfy both the criteria, then the sand is, particular sand is called as a indicated as SW, that is well graded sands or gravelly sands with little or no fines. So, SW listened indicates a well graded sands, or it can be gravelly sands, little or no fines. Similarly, the poorly graded sand, gravelly sands, a little or no fines is indicated as well listened SP. The deduction for this if you are not able to meet the above two criteria, like if the Cu is say less than 6 and Cc is not in the range of 1 to 3, then it is not actually meeting the criteria for qualifying for SW, then that indicates that the group or legend should be SP. So, poorly graded sand, gravelly sands, little or no fines. Sands with fines, appreciable amount of fines, that means silty sands, sand silt mixers SM, again here the plasticity index is less than 4 and falling below the A line, then in that case silty sands or sandy silt mixers SM. Clayey sands and sandy clay mixers SC, because the Atterberg limits above A line with the plasticity index greater than 7. That means, the plasticity index and liquid limit if you take and it falls above A line, that means that the origin of this is because of the plasticity index is greater than 7, that is clayey sands and sandy clay mixers. So, SC group indicates that clayey sands are sand clay mixers. Silty sands, sand silt mixers indicated by SM. Now, having seen coarse grained soils, let us look into fine grained soils. The fine grained soils, again the percentage passing number 200 C is greater than 50%. So, as we said that the two groups, coarse grained soils and fine grained soils. So, in the previous two slides we have seen the criteria of classification for coarse grained soils. Now, we are looking for the classification chart for fine grained soils. So, fine grained soils, the percentage passing number 200 C is greater than 50%, silts and clay liquid limit is less than 50. So, inorganic silts with very fine sands, rock floor, silty or clayey fine sands are indicated with ML, that is silt of low compressibility. The plasticity chart. Inorganic clays low to medium plasticity, gravelly clays, sandy clays, silty clays, lean clays, they are indicated with legend CL. Organic silts, organic silty clays, low plasticity OL. So, OL indicates that organic silts with low plasticity, organic silty clays with low plasticity, they fall under this particular classification with legend OL. CL indicates that inorganic clays of low to medium plasticity. Sometimes the borderline cases they do exist. Basically for in the plasticity chart, it is known for some low plastic soils CLML. CLML indicates there is a borderline case which lies above the A line, which exhibits with the low plasticity as well as some clay fine characteristics. So, the criteria of classification is plasticity chart. We have already discussed about the plasticity chart. The same plasticity chart is used to arrive at these classification systems. To get these things, depending upon the silt and clay and the liquid limit, Atterberg limit test results, when putting on the plasticity chart, we will be able to tell what type of soil it is and what type of legend it is eligible for. So, next major division is silt and clay, liquid limit is greater than 50. Previously, we have seen the fine grained soil with the liquid limit less than 50. Now, we will be seeing the silt and clay with the liquid limit greater than 50. So, inorganic silts, micaceous or diatomaceous fine sandy silty soils, elastic silts, that is MH. Inorganic clays, high plasticity, fat clays, CH, that is indicated by that is inorganic clays of high plasticity, they are also called the fat clays, is called CH. Organic clays medium to high plasticity, organic silts OH. So, if the liquid limit is greater than 50, then they are divided again into MH, CH and OH subgroups and with the different soil classification symbols. Similarly, highly organic soils, peat, mulch and other highly organic soils, so they are called as indicated as P suffix T. So, highly organic soils, that is the third subgroup which we have discussed earlier in the extended Casagrandes classification system, which is highly organic soils, which is peat, mulch and other highly organic soils, which indicated as PT. So, we have seen criteria of classification for coarse grained soils and fine grained soils. So, based on the grain size distribution and Atterberg limit test results, by using these two results and by using this criteria, one can classify the soils into different groups like CL, ML or CL, ML depending upon the eligibility for the borderline cases, or CH, OH whether they are above the A line or below the A line, or in doubtful cases to distinguish whether the soil is organic or not, if one can conduct a liquid limit to find out whether decrease in the liquid limit is there or not. If the decrease is more than or equal to 30%, that indicates that a soil is organic. Now, look into the classification based on the percentage of fines, the percentage passing number 200C. For example, we have discussed that while discussing relative density test, we said that if the fines are more than 12%, then different field density criteria are required to be used. If fines are less than 12%, we also discussed that they may not be required to carry out hydrometer analysis test and all. So, the percentage of the passing number 200C, say less than 5, then the classification reduces to GW, GP, SW, SP, and greater than 12 GM, GC, SM and SC, and between 5 and 12, that is they are called the borderline cases. Borderline dual symbols are required. Suppose if you have got 5 to 12, then such as GW, GM, GW, GC, GP, GM, GP, SC, SW, SM. That means that well graded sand and sand with some amount of silt. SW, SC, SP, SM, SP, SC. So, these are the borderline cases which are indicated for the percentage of the passing is between 5 to 12. If it is in less than 5, then is a clear cut case for us, GW, GP, SW, SP. If it is more than 12, then GM, GC, SM, SC. Atterberg limits above A line and plasticity index between 4 and 7 are borderline cases, and it needs dual symbols. So, that is what where that CL-ML classification will come into picture. So, let us once again, having discussed about the Casagrande's plasticity chart, let us look into this chart once again. We have seen that here the plasticity index is indicated here and the liquid limit is indicated here. Here along this line, equal plasticity index but increasing liquid limit, and here equal liquid limit and increasing plasticity index. So, for a liquid limit of 120%, soil is exhibiting and increase in the plasticity index. So, here this line which is above A line, which is limits for the group of the samples of the same geological origin fall on line approximately parallel to A line. So, different samples from the same soil stratum, they are exhibiting the similar characteristics you can see here. So, CL, ML, OL. So, this is that borderline case which is with the plasticity index between 4 to 7. So, you can see here CL, ML which is the borderline case here. Some coarse grained soils or sandy soils also they fall here. CL which is clay of low plasticity which is indicated here, ML or OL which is indicated here, and CH clay of a high plasticity which is shown here, and MH or OH, this is organic silt of high compressibility, and this MH is inorganic silt of high plasticity which is placed here, So, having seen the soil classification system, let us apply this knowledge for solving the some 3 typical problems. So, problem 1 which is basically is the results of grain size distribution analysis were given and some Atterberg limit test results were given. So, in the problem 1, the statement states as follows: for a soil specimen, the given are passing 2 mm sieve, percentage passing 2 mm sieve is 100%, passing 0.42 mm sieve is 85%, passing number 200 sieve is 38%. So, that is less than 50%, and liquid limit is 20% and plasticity index is 12%. Classify the soil by the unified soil classification system. So, we were asked to classify the soil for the given data of the soil which is given. This has been obtained from the laboratory analysis. So, the problem solution for the problem works out like as follows. Since the soil is a coarse grained soil, because the percentage passing number 200 C is less than 50%. So, if it would have been more than 50%, then the first step itself would have divided that into a fine grained soil, but it is eligible for the coarse grained soil because the percentage passing number 200 C is less than 50%. So, sands, basically it is sand because percentage of the coarse fraction passing number 4 C is greater than 50. So, that is eligible for a sand. Since more than 12% passes number 200 C, it must be SM or SC. So, since more than 12% passes through number 200 C, that is 75 micron C, then it must be SM or SC. Now, we have to decide which one is eligible for the classification legend. So, here it was given to us plasticity index is equal to 20 minus 12 liquid limit minus plastic limit is equal to 8, which is greater than 7. So, if it is greater than 7, that is above A line. So, above A line carries with the group called C. So, the soil classification is SC. SC indicates this is the soil classification which is obtained here. So, this is the problem which is having a coarse grained soil, the percentage of passing number 200 C is less than 50%, and the sand with a percentage of coarse fraction passing number 4 C is greater than 50. So, in the problem 2 is a typically different problem. For a soil specimen, the given are the passing number 4 C, that is 4.75 mm is 92%, passing number 40 C, that is 0.425 mm C is 78%, passing number 10 C is 81%, passing number 200 C is 65%, and Atterberg limits are liquid limit is 48% and plasticity index 32%. So, we are required to classify the soil based on the unified soil classification system. So, if you look into it, since more than 50% of the soil passing through a number 200 C, so it eligible for a fine grained soil. So, it could be ML, CL, OL, MH, OH, CH or OH. So, beginning we will not be knowing what type of soil classification it is going to get. Now, by using now the liquid limit and plasticity index values, we can ascertain the group of the soil. So, if you plot liquid limit 48 and plasticity index 32 on the plasticity chart, then it falls in the zone CL. So, the eligible soil classification is now CL. So, soil is classified as CL. Now, these two problems which are discussing about the type of a coarse grained soil and then fine grained soil. So, similar types we should use for classifying borderline cases also, like two eligible symbols like GW, GM and other cases. So, one should use this criteria and strictly and follow this criteria and to arrive at the classification legends of the soils. Let us look into the third problem. This is the soil classification system by using the activity number. Here we were given liquid limit of a given soil, that is 67% and plastic limit as 32%, and clay fraction was given, which is 80% of the sample consists of the particles smaller than 0.002 mm. From this information, we are required to classify the soil based on the activity and indicate the probable type of clay mineral. So, the solution works out like this. We knew that activity is equal to plastic index by clay fraction, plastic index is equal to liquid limit minus plastic limit. So, from this you determine plasticity index, which is 35%, and percentage clay fraction, which is given as 80%. So, activity is equal to 35 by 80. 35 by 80, which is 0.44. So, if this value is now is less than in the range of say 0.3 to 0.5, we have discussed that. This value also indicates the probable clay mineral, that is we have seen it indicates the probable clay mineral as a kaolite. So, based on this data, the indication is that the probable clay mineral in the soil is kaolite, because it is exhibiting low activity with the ratio of plasticity index to percentage clay fraction. So, In these lectures with index properties with soil classification systems, total we had 5 lectures. What we have tried to see is that we tried to determine the different index properties of soils like specific gravity, water content, other index properties of a soil, Atterberg limits for fine grained soils, and then we also discussed about different methods for determining coarse grained, arriving at the sieve analysis or a mechanical analysis of gradation of the soils, basically sieve analysis and fine sieve analysis, and for hydrometer analysis for the fine grained soils. Then we used all this data which we have generated from these properties to classify the soils or to group the soils which are exhibiting identical characteristics. So, with this information it will be possible for us to classify the soil.